If you have built any LLM pipeline recently, you know the absolute nightmare of information extraction. You feed an LLM a massive 50-page clinical report, ask it to extract medication, and it does. But it slightly paraphrases the text, maybe hallucinates a word or so, and then suddenly you have no idea where it comes from the original document. No character spans, no traceability. For the last 10 years of my career building AI system in the real-world industries, this lack of grounding has been the #1 blocking for production. During my PhD times, we used to spend weeks on fine-tuning custom name entity recognition model just to extract the character spans. But Google just quietly open sourced a 10,000-line Python library called LangExtract, and it completely flipped the script. So it uses few-shot prompting to extract anything that you want, but it forces the LLM to map every single entity back to exact character level span in the source text. Today, we are going to pop the hood on this library. I'm going to show you the 4 clever engineering pillars Google's use to tame the LLM beast. And honestly, the algorithm they use for pillar 3 is the masterpiece in optimization. So without further ado, let's jump right into it. Welcome everyone to our channel, AI Fun Fact for All. For those of you who are in this channel, my name is Pedram, I have a PhD in computer science, and in this channel we talk about AI and machine learning and how we can use it in order to improve our efficiency. So on #1 pillar, I want to talk about the smart chunking. So if you just chunk the text arbitrarily every 1,000 characters, you slice right through the words and sentences. So the LLM loses the context and obviously the extraction fails. LangExtract solved this by highly optimized chunk iterator. It tokenized the text not with an LLM BPE tokenizer, but with a fast regex or Unicode tokenizer, and greedy packs the whole sentence into the buffer. What happens if the sentence is longer than the buffer? Instead of breaking randomly, it has a heuristics that hunts for most recent new line character. In clinical or legal docs, new lines usually mean a new section. And they also try to solve the cross-chunk conference problem. For example, let's say the chunk 1 say Dr. Johnson and chunk 2 say she predicted something. So LangExtract injected trailing character into the previous chunk directly into the prompt. So it is very simple, but it actually perfectly preserves the semantic continuity. Moving on to pillar #2 is schema enforcement. Getting a JSON out of an LLM is a very hard task. So LangExtract does something brilliant here. You don't want to write JSON schemas, you just provide 1 or 2 Python example of what you want to extract. So the library inspects your examples and automatically bootstrap scripts OpenAI schemas. So basically it follows the code first architecture. It also uses a really clever flat schema trick. Instead of deeply nested JSON, which LLM actually struggle with, it uses underscore attribute suffix. So you get a flat extraction like medication and a per dictionary like medication attributes. This flattens the generation tree and basically drastically reduce the hallucination. Alright, pillar 3. We are on halfway mark, and this is the absolute coolest part of the code base, the alignment engine. So the LLM give you the text, but the LLM are terrible copiers. They add articles, change prioritization. How do you map medications back to medication at the exact character position 405 to 415? Google built a 3-tier fallback algorithm. So in tier 1, it uses Python sequence matcher to find the exact token sequence matches. In tier 2, if accepts lessers, partial matches if the LLM hallucinates extra words. And in tier 3, if all of them fails, it falls back to a sliding window fuzzy match. Now, a sliding window fuzzy match on a massive document usually results in catastrophic O n squared m time complexity, so it is actually very slow. But Google engineers use a brilliant shortcut in here. Before they run the expensive sequence matcher, they do a O1 pre-check on using a Python counter intersection. As a window slice across the source text, it just check, are there enough matching tokens in this window? If the intersection overlap is below 75%, you skip the math entirely. So it transforms a very heavy on a scalable algorithm into lightning fast grounding engine. Finally, plan number 4, boosting recall. So LLM are stochastic. Sometimes they miss an entity on the first pass. Instead of cracking up the temperature, which just increases the hallucination, LangExtract uses a multi-pass strategy. It runs the exact same document through the LLM 2 or 3 times at the lower temperature and then runs a first pass wing merge. So it looks at the character intervals, and if a new extraction doesn't overlap with an existing one, it merges it. You will pay a little bit on API cost, but your recall shoots through the roof, and duplicate extraction are mathematically impossible. And there you have it, guys. By combining a smart sentence chunking, auto boosted schemas, and O1 optimized fuzzy alignment engine, and a stochastic multipath merging, LangExtract gives you the holy grail of unstructured data, LLM reasoning with exact character level traceability. So no more black box extraction. If you're building AI agents in a compliance heavy industry, you need to be using this kind of architecture. As I mentioned, it is completely open source, and I've linked the Google GitHub repo in the description, so go ahead and read the resolver.py file. It will make you a better engineer overall. If you found this breakdown helpful, hit the like and subscribe. It lets me know that you're interested in this kind of content, and I'll make more videos like this. And if you enjoyed this video, I think you also like this one that I talk about LangGraph versus vector database. You can watch this one that Meta shows to train a model with only 13 parameters. Thanks for watching, and see you until the next one.